So here we have a set of three-dimensional vectors, and we're meant to determine what F3 needs to be so that our system is in equilibrium. So what's happening here is that we have some particle at point O, which represents our origin, and it is in contact with three forces that are acting through that same point. So this is some sort of concurrent force systems. And what we have here is F1, which is given by its vector 4i minus 2j plus 3k. And we have F2, which its vector is minus 6i plus j plus 2k. And the third vector is what's unknown, but we need to determine the components of the third vector so that the system is in equilibrium, meaning it's balanced. So let's do that. Now, in order for a system to be in equilibrium, we know that its forces must be balanced in all directions. So that's the condition that we have to set for equilibrium. So what should happen here is for F1 vector, when we sum these up, so F1 plus F2 and plus our unknown vector, which is F3, if these three forces are in equilibrium, then these should sum to give 0. So what we're going to do is apply this condition to set out what we expect to get for that third vector. So therefore, what we need is F3. And if we were to write this in vector form as it's unknown, then what we would have is some x value, I, plus some y value, j, and plus some z value, k. So what we really need to find really is x, y, and z. So how we do that? Let's sum these components then. So we will have 4i, and that 4i is coming from the F1 component, and minus 6i, and plus our unknown, which is our xi component. So all of these should be equal to 0, because once again our forces must be balanced in all directions. So then what we end up with for our x value here, so therefore our x value here must be equal to 2. Now let's apply the same principle for the j components. So what we have is negative 2j plus 1j and plus yj. That equals 0. So if we were to sum negative 2 plus 1, then that gives us negative 1. So therefore, to balance this, y must be equal to a positive 1. So just to recap here, if we go back to the x value, how we got that 2, if we were to sum this 4, this negative 6 here, then that would give us a negative 2. And when we rearrange this equation, then x would be equal to positive 2, because it's only positive 2 we can really add to negative 2 to get 0. And it's the same thing we applied there in the purple writing. So on to the next one then. So for the k component, so we're going to have here 3k and plus 2k plus, this is a zk, and this should be equal to 0. So therefore our z value is going to be a negative 5, because when we do 3 plus 2, that's a positive 5. So to ensure that this equals 0, we have to sum with that a negative 5. So then our final answer is us putting together all of the sums that we have here. Just going to clear what's at the very top to fit that answer. So F3 is going to be equal to our first component there for x, so that's going to be 2i plus we got 1 for the y component, so 1j, and negative 5k. And this represents our F3 force vector. So that's it. Hope you have found some value from this video, and we're going to continue this series, so check out this next video right here.